Hi everyone, welcome to the course on Microsensors and Nanosensors. We are in the sixth module of this course where we are discussing the temperature sensors, and today is the fifth lecture of this temperature sensor series. In this, we will be discussing today mostly semiconductor based sensors and IR based optical temperature sensors. The first discussion today is on semiconductor PN junction temperature sensors. All of you are aware of what is a p-type semiconductor, what is a n-type semiconductor, how a PN junction is formed. Okay, if you are not aware, I will suggest that you go through some literature on semiconductor junctions, particularly PN junction. There can be other junctions also in semiconductor devices, but let us discuss the PN junction very quickly so that it is refreshed in your mind. Okay, so you know that how a p-type semiconductor is generated and how a n-type semiconductor is generated, right? So in a silicon, when you populate it with electron by introducing a defect in it, okay, we generate a n-type semiconductor, right? So say if the silicon is a group 4 element, okay. So if I dope it with some group 5 element, okay, basically I am populating it with one extra electron, which make it a n-type semiconductor, right? And if I dope it with a group 3 element, we generate a p-type semiconductor, right? This is as simple as this, okay. For elaborated discussion on this, you can refer to any textbook on semiconductor material and semiconductor devices. Okay, so you can understand that when I have a p-type semiconductor and a n-type semiconductor, I can always create a junction. Okay, when they are kept together, right? Usually, it is done by doping, say, this is a p-type semiconductor. Usually we do dope it with some n impurity and we have this PN junction, right? Usually these are metallurgical junction, okay. The p-type semiconductor has excess holes while n-type has excess electrons, right? At the junction, electron and hole diffuses from p side to n side and n side to p side, and in this process, a depletion region is created, right? So, either electron can move from n side to p side, or hole can move from p side to n side, okay? And this is mostly done by the process we call it diffusion. While there can be drift currents also, where electric field in depletion region opposes the any further diffusion, okay? And current has a natural movement, it is the drift current, okay. And then there can be a equilibrium condition when drift and diffusion currents balances them out, right. Now this PN junction, okay, you might have read about diodes. We are not going to discuss that in detail because this course is not about actually diodes or any semiconductor devices, but what we are trying to do is we are trying to utilize this junction for temperature measurement, right. So in the forward bias condition, when I say forward bias condition means this p-type is connected to a positive terminal while this n side is connected to the negative terminal of a battery, okay. Under this forward bias condition, external voltage reduces the junction barrier which is formed at the p and n junction, okay. And when you are under this condition of biasing, this depletion region thickness decreases, okay, and this will allow current to flow, okay. Under the reverse bias condition, external voltage increases this barrier or the depletion width will increase, okay. This will prevent the further current to flow in the device, okay, or in the circuit, okay. Usually the reverse saturation current is very small, particularly if you ideate a diode's behavior, okay. Now what our aim is to utilize this PN junction for a temperature sensor. Okay. So, a PN junction temperature sensor uses the properties of a diode to measure the temperature, and the diode that is under discussion is the PN junction diode. Okay. So, when forward biased, the voltage across the diode varies with the temperature. We will see the equation, okay, but for the time being you can understand that when the diode is under forward bias condition, the voltage across the diode varies with the temperature. Okay. This PN junction they are commonly used in ICs and thermal management system. We will see some more utilization of this PN junction temperature sensor. Okay. The forward voltage of a PN junction diode basically decreases linearly when temperature is increased. Okay. And this decrement rate is around -2 millivolt per degree Celsius. Okay. So, with a constant forward current, temperature can be determined from the voltage drop. Okay. So, when there is a constant forward current, temperature can be determined from the voltage drop. So, it suggests that there should be a constant forward current. When you require a constant forward current, basically what I am asking you to have a constant current source. Okay. Constant current source. You might have seen that the transistors can be biased in a different configuration, including it can also be biased in such a condition that it acts as a constant current source. So, that kind of constant current source can be used for biasing this so that temperature can be determined from a voltage drop. Okay. So, semiconductor PN junction in both the cases, be it diode or it's a bipolar transistor, both exhibits a significant thermal dependence. Basically, if you see, in both the cases there are junctions, PN junctions, okay, which are when forward bias with a constant current source, they can act as a temperature sensor. Okay. So, when a constant current generator is applied to forward bias junction for both the cases, okay, the resulting voltage indicates the measure of the junction temperature. Okay. So, a key feature of such sensor is its strong linear response. You can see one of the response that for silicon at different constant currents, okay, you can see that the sensitivity is around -2.3 millivolt per degree Celsius, while for decreasing this current several times it increases to -2 millivolt per degree Celsius. Okay. So, the current voltage relationship of a PN junction diode, we all know the popular diode current, which is a Shockley equation. I is equal to I naught into e power QV by NKT minus 1, right, where Q is the charge, this V is the applied voltage, okay, then K is the Boltzmann constant, and all these notations are known. Okay. The temperature dependent voltage across this junction can be given by V equal to Eg by Q minus 2 kT by Q into ln K minus ln I, where Eg is the energy band gap for the silicon, Q is the charge of the electron, and this small k is the Boltzmann constant, while this k is a temperature independent constant, and this constant is basically related to the material, okay, and I is the current. Okay. So, this is the temperature dependent voltage across the junction. Okay. From this equation, it follows that when the junction operates under constant current condition, the voltage varies linearly with the temperature, because the other term is a constant, and its slope can be given by differentiating this equation with respect to temperature. So, if you differentiate this, V equal to Eg by Q minus 2 kT by Q into ln K minus ln I, okay, if you differentiate it with respect to temperature, you get the slope, and the slope can be given as dV by dt, which is 2K by Q into ln K minus ln I. All right. So the slope can be given by dV by dt, which is equal to 2k by q ln k minus ln I, and the value that you have just seen on the curve, minus 2.3 millivolt per second or minus 2 millivolt per second, comes from this slope. Okay. So typically for a silicon junction operating at 10 microamp, the slope is around 2.3 millivolt per degree Celsius, and this decreases to approximately 2 millivolt per degree Celsius when the current level is around 1 milliamp. Okay. Now there is a concept of IC temperature sensors which is available in the form of integrated circuit. Okay. So in a semiconductor PN junction, this current through the junction is proportional to the temperature when voltage is constant, or for a constant current through the junction, the voltage across it is a function of temperature. Okay. Similar to this, we have for transistor, the voltage across the junction between the base and emitter depends on the temperature and can be used as a measure of temperature. Okay. So a commonly available technique uses two transistors operating at different collector currents with the temperature determined by measuring the difference in their base emitter voltages. Okay. So this kind of transistor can be used in circuit with other components to behave as a temperature sensor. Okay. So the IC temperature sensor is very crucial, and mostly they are inspired by this transistor based devices. Okay. So LM35 is the common temperature sensor whose output voltage is linearly proportional to the temperature. Okay. It usually provide the accuracies in the range of plus minus 0.25 degree Celsius at room temperature, and if you consider the complete temperature range, which is usually from minus 55 degree Celsius to 150 degree Celsius, this accuracy is around plus minus 0.75 or 0.75 degree Celsius. And please note that this is without any external calibration or any external trimming. Okay. So this IC temperature sensors has various advantages. For example, they have low output impedance. Okay. Their output is linear and precise inherent calibration is available in this kind of IC temperature sensors. So this type of temperature sensors are very easily integratable with the interface and is available with control circuitry and other things. Okay. So LM35, the popular IC temperature sensor, can provide an output voltage directly proportional to the temperature scale factor of around 10 millivolt per degree Celsius with an operating range of as I have mentioned, minus 55 degrees Celsius to 150 degrees Celsius. Okay. Then there are some IC temperature sensors specific to some companies like say Analog Devices. They have very popular IC temperature sensors like AD590 and AD592. Okay, they are a very good example of IC temperature sensor which convert the temperature to current levels. Okay. So these AD sensors usually operate with a voltage level of 4 to 30 volt DC supply and produce the output current which is linearly proportional to the sensor's temperature. Okay. So the application of these IC temperature sensors are enormous. Okay. In the microprocessor and IC thermal monitoring, mostly these IC temperature sensors are used, but nowadays they are very popular in the battery management systems. Okay, particularly with the rise in EV, you can see that all of these battery management systems are integrated with this temperature IC temperature sensors to monitor the rise in temperature when the battery is in operation. Okay, then they are very popular in the industrial temperature control. Okay. In the consumer electronics and wearable devices, this IC temperature sensors has found its application. Okay. In automotive system, usually it find its application partially because it cannot go beyond 150 degrees Celsius, or the performance is mostly non-linear beyond 150 degrees Celsius. It is partially used in the automotive system, okay, but it is very popular in the medical devices and IoT and smart home systems, okay, where the temperature is expected to not rise beyond 150 degrees Celsius, okay. The advantage of this IC temperature sensors are their small size and easily integratable with the existing CMOS technology, okay. And some of the IC sensors are actually fabricated based on TTL technology, so it is also compatible with that particular technology, okay. The low cost and low power consumption of these IC temperature sensors are very fascinating, and batch fabrication actually enable it to be utilized in low power or in low cost devices, okay. The response you have seen is mostly linear, okay. So you do not have to put extra effort to dig out the linear response from a non-linear response. So the linear response of this IC sensor is very advantageous for many circuits or many applications, okay. And this kind of temperature sensor provide you the linear response, but at the same time it maintains the good accuracy, okay. And that's why you have seen that the application of this IC temperature sensor is really vast, okay. However, they have certain limitations, like the limited temperature range compared to the industrial sensor is one of the disadvantages. So till now I think we have not seen any sensor which has this limited range of say minus 55 degrees Celsius to only 150 degrees Celsius, okay. And although many of this sensor has integrated calibration system, but they require calibration for high precision application very frequently, okay. And since this IC temperature sensors are available in both type, it is available in analog form as well as in digital form. So most of the analog devices, the analog IC temperature sensors are very susceptible to noise, okay. So you have to take care of that also, particularly for when you are struggling to measure low temperatures in low current levels in your circuit, okay. So this is the IC temperature sensor, okay. Then there is one more type of temperature sensor which has found its application in this COVID arena, and we all might have seen this kind of thermometer regularly, that is IR temperature sensor or IR thermometers, okay. So an infrared temperature sensor is a non-contact device. So I am sure that you might have seen the people checking the temperature from little far. So it's a non-contact kind of device. You don't have to actually take the thermometer to the patient or to the person whose temperature has to be monitored, okay. So because it is a optical kind of device, so an infrared temperature sensor is a non-contact device that measures the infrared radiation, or it is also, you can understand it as a heat energy emitted by an object to determine its temperature, okay. And it is available in various form factors. Some of them I have demonstrated over here, okay, but this is just limited. It is available in several distinguished form factors, okay. So the basic concept is either you if a body is heated, okay, it will emit some infrared light. So either you detect it directly, or you use transmitter and receiver kind of system where IR transmitter is emitting some light, and it is falling on the object, and based on the intensity or other parameter that IR receiver receive, okay, we can comment on the temperature of the object. But this object is self-sustainable to emit heats, okay. So it has already the capability of emitting heat, because everything we know is at a certain temperature. Our body is maintained at certain temperature. Similarly, if you talk about any object, they emit some IR. So it can be directly received by a specified, special kind of IR receivers. Okay, we may discuss this IR receiver in more detail in our coming lectures. Okay, so this is the spectra, the complete spectrum, including the radio waves, long radio waves, IR, X-ray, UV and gamma rays. Okay, and we are in this lecture we are interested in the IR rays. Okay, so the infrared wavelength range spans from approximately beyond 700 nanometer, and you can expect it to go to millimeter. Okay, so it is typically divided into several sub regions. Okay, and in broad, usually you have NIR, which is near infrared, and typically it ranges from 700 nanometer to 1.4 micron. Okay, then you have short wave infrared, we call it SWIR, which is from around 1.4 micrometer to 3 micron. Okay, then we have mid-wave infrared or MWIR, which ranges from around 3 micrometer to 8 micrometer, and then you have long wave infrared, we call it LWIR, it ranges from around 8 micrometer to 15 micrometer, and then you have the FIR, which is far infrared region, which is anything beyond 15 micrometer, and it spans to around a millimeter. Okay, however, this definition is very broad, and it is not exhaustive. Okay, and there can be a little variation from one textbook to another textbook. Okay, so I think we should not worry much about it. Okay, somewhere you may find that infrared is an electromagnetic wave whose wavelength belongs in the range of around 760 nanometer to 1 millimeter. Okay, anything between visible light to microwave. Okay, and the broad division of infrared is just on 3 parameters, in 3 different types. Either it is near infrared, mid infrared and far infrared. So the other things that we have seen, short wave infrared, mid wave infrared and long wave infrared can be another kind of classification. Okay, so we should not worry much about this. So near infrared is anything from 760 nanometer to 3 micron, mid IR is anything from 3 micron to 50 micron, or far infrared is from 50 micron to 1 mm. Okay, so definitions can be exhaustive. However, in this course we will be following these notations. Okay, so near infrared anything from 700 nanometer to 1.4 micrometer, then short wave infrared anything 1.4 to 3, mid is 3 to 8, long is 8 to 15, and far is 15 micrometer to 1 millimeter. So we will be utilizing this particular notation throughout the course. All right. So I was coming to this IR temperature sensor. As I was mentioning that every object emits IR radiation depending on its surface temperature. So the hotter is the object, the more IR radiation it emits. Okay, the IR temperature sensor uses a IR detector to detect this radiation. Okay, mostly thermopile sensors are used. Thermopile can convert this IR radiation to heat, and this can be detected by converting it into a voltage by using a thermoelectric effect. Okay, this voltage is proportional to the intensity of the IR radiation. Okay, so the generated voltage usually is very small and is amplified by the internal electronics. Okay, usually a microcontroller converts this analog signal into a readable digital temperature values. Okay, the advantage of IR sensors are the first advantage of course is the non-contact measurement. So you do not have to actually touch the person to measure the temperature. The response time is high. Okay, and the accuracy of the sensors are good. Okay, There measuring range is also very high, because you do not have to be in the contact. So, it is a non-contact temperature sensor, and I mean, you can have, depending on the detector and the emitter, okay, you can have good range of measurement. Okay. Then you have energy efficient IR temperature sensors available. Okay. So, for non-contact temperature sensing, mostly these IR temperature sensors are utilized, while for on-chip measurement of temperature, particularly in the industry automation or for automobile sector, okay, these IC temperature sensors are utilized. Okay. So, we have tried to cover both kind of devices in brief. Okay. In the next classes, we will be starting the discussion on the force sensors. Thank you.